A double displacement reaction occurs when two soluble reactants are mixed together. The reactants dissolve into their ions, and the ions swap out to form new ion pairs that are the products. The animation shows how this happens. There are four possibilities for a double displacement situation. 1. No reaction. Identify both products as aqueous and recognize that the result is just a beaker of ions. 2. Neutralization. Identify the products as an ionic compound and liquid water. Identify reactants as an acid and a base. 3. Precipitation. Identify one product as a solid. And 4. Gas evolving. Identify one product initially as either H2SO3 or H2CO3. And notice that these products are not stable and will decompose into liquid water and a gas. In order to solve these problems, you must be able to identify ions and their charges from chemical formulas and be able to recombine ions to form new chemical formulas. Please accept that these are important and necessary steps, but recognize that the strategy is the same every time. The only exception is if one of the products is initially sulfurous acid or carbonic acid, like mentioned earlier. So let's jump right in with an example. We're given the reactants of aqueous aluminum nitrate and aqueous sodium carbonate. The first step is to write the ion pairs for the reactants. So for aluminum nitrate, our ions are Al3+ and NO3-. For sodium carbonate, our ions are Na+ and CO3 2-. Now we'll rewrite the cations over on the product side. So we have Al3+ and Na+. But now we'll swap the anions. So now carbonate will pair with aluminum and nitrate will pair with sodium. To combine the first ion pair into a chemical formula, we'll ask the question, does 3 equal 2? Are the charges equal and opposite? And the answer is no. So we'll have to switch the charge values over to serve as subscripts. And when we do that, the first chemical formula will be Al2 CO3 3. For the second ion pair, we'll ask the same question. Are the charges equal and opposite? In other words, does 1 equal 1? Here the answer is yes. So these two ions combine 1 to 1. And we just write them down as NaNO3. Now we'll use our solubility rules to identify the phases of our product compounds. For aluminum carbonate, we locate carbonate on the solubility rules. We move over and we see that most carbonates are insoluble, and aluminum is not an exception. So the phase here is S for solid. For sodium nitrate, we notice that all sodium compounds are soluble and there are no exceptions. So this phase is aqueous. We're almost done. Now it's time to balance the chemical equation. So we'll start by keeping track of how many of each element we have below our unbalanced chemical equation. And we'll go ahead and track the polyatomic ions as groups. So we have 1 aluminum and 3 nitrates, 2 sodiums and 1 carbonate on the reactant side, and 2 aluminums, 3 carbonates, 1 sodium, and 1 nitrate on the product side. Now for the balancing. We have 1 aluminum on the reactant side, 2 on the product side, so we need to put a 2 out in front of aluminum nitrate. That changes our aluminums to 2 and our nitrates to 6, and our aluminums are balanced. Next, we have 6 nitrates on the reactant side, 1 on the product side, so we add a 6 in front of sodium nitrate on the product side, and that balances our nitrates at 6 and 6. Finally, we have 1 carbonate on the reactant side, 3 carbonates on the product side, so we need a 3 out in front of sodium carbonate, That changes our sodiums to 6 and our carbonates to 3, and our sodiums and our carbonates are balanced. So our final chemical equation is 2 aluminum nitrates plus 3 sodium carbonates goes to 1 aluminum carbonate and 6 sodium nitrates.